Very welcome everyone to our next session in the Fractal Geometry Seminar. And our next speaker will be Gergő from Corvinus and Rényi, and he will talk about bisymmetry and continuity.
Yes, so thank you very much for the kind invitation. So today I would like to talk about a slightly connected topic, which is based on functional equations. And it is a partial joint work with Pál who's working here at this moment, and Patricia Sokol from Debrecen. So let's start with some algebraic properties. So let X be a set with at least two elements. Just this definition is meaningful. And we take a function from x squared to x to itself, and we say that it's reflexive if we put x twice there, then we get back x. It's a very strong condition, seemingly. Symmetry, if fxy is equal to fyx for all xy. Next, and bisymmetry. Bisymmetry is defined by this equation, but if you see that what's happening is just shifting these two a variable, not shifting, changing these two variables, and it inherits some. Okay, I write something. Let's try.
Yes.
So this is this type. This we can think on that we write x, y, u, v in this way, and first we evaluate by rows and then by columns, the results by columns, and it says that it is the same as we. Okay, I try this. As we evaluate first these, I'm not sure that it's visible at the end, and then we evaluate this, and this value is the same. So it's kind of commutativity assumption. And so this is one of the basic properties, and we have some analytic properties. So now we take an interval, a proper interval, and we assume, usually I assume that it is closed. It's a technical condition, sometimes not, sometimes yes. So, but let us assume for a while that it is closed, and then we take a function. Now it's not a. I say it is a operation if it's from I to I times I to I, and if it's I times I to R, then it is just a function I refer. So I distinguish in this case, but
which is the operator? Sorry, what is the difference?
Operation. Operation is when this is an I, so it goes to itself. Okay, and I said that f is, and I have several different quantities. So f is partially strictly monotone, partially strictly increasing, partially monotone, partially increasing. If the sections has this property, so if we fix x, the second variable, then in the first variable it is. Or I fix the first variable, and in the second variable, it is strictly monotone, strictly increasing, monotone increasing for all fixed x0 and y0 and I. Okay, continuity, I think is clear, so I will not define. And yeah, I will talk about some mean property. So let's define what is a mean. A mean is when fxy is in between the minimum and the maximum of the two values. So let it's strict if there is no equality. So
it's unless they are the same.
Sorry?
Unless they are the same.
But if they are, yeah, that's a very good point. So if x and y is the same, then I get automatically reflexivity, and you can build up some.
Yeah, so you cannot.
Yeah, you're right. So yeah, strict means that when x and y are different. You're right. I understand. But also there are some small statements which I avoid now. That, for instance, if you have reflexivity and strict increasingness in two variables, then you get a mean. So you can prove that. Okay. Yeah. Oh, I have it. So I do not avoid. Sorry. So I want it just. So this is the first statement which I said. The second one is when you have reflexivity and partial monotonicity or partial strict monotonicity in two variables, it implies increasingness, but it's not the case anymore if you go further in three variables. And a very simple example is just x plus x plus y, x minus y plus z is increasing in each of the variables, and if I write x, then I get x. So it's clear that it's reflexive, so it's not true anymore. These are the two tiny statements, facts. And this has a long history, this part, but I just focus on very short part because functional equationists, if there exists this word, they are more interested in this part. So I think it's better if I just focus on the clear background. So the first thing is the characterization of the quasi-arithmetic means, and it is this found by this statement, which I will talk about, found by Kolmogorov. Okay, I write in two different ways, but Kolmogorov, Nagumo, and Definetti at the same time. So it's he's from Japan, he's Italian, and he's Russian for sure. So they said that the quasi-arithmetic mean for them is a sequence of functions. So now I step out from the two variable case for a while. From I to the n to I for each fn, they have the following property that it is strictly increasing in each of its variable and a continuous function. So they take a strictly increasing continuous function, one variable function from 0, 1 to I, such that fn can be written in this form. So this is just the definition. If fn satisfies for all n this type of expression, then we talk about quasi-arithmetic sequence or mean in this sense. What does it mean? So we basically conjugate the usual arithmetic mean by a function f. The interesting part of this is that many mean what we define is involved in this class. So that's why it is interesting and important. And also, okay, let's go further. So how we can characterize this? And this is what they did, separately from each other. So the characterization of this type of sequence Fn can be given in the following axioms. So Fn is continuous and partially strictly increasing and reflexive for all n. This is the first immediately three different condition. Fn is symmetric for all n, and it has some property which is they called associativity, but some of them called associativity. Associativity we use in a different meaning. So I would say if you substitute the case term for the first k times, and then the rest is the same as the original. So if you remember the proof of arithmetic and geometry inequality, we use this type of trick in the inductive proof of that. Okay. So they said that if you have these three properties, then it is a quasi-arithmetic mean. So it satisfies that condition. You can find the one variable function f, so that it is all fn is a conjugate form. And now I write with blue continuity. I don't know whether we can eliminate continuity in this terminology, but what I will talk about is the two-variable version. So János Racév is one of the big five member in 48. He proved the following. He introduced bisymmetry. He was the first who technically introduced bisymmetry, and that's why I wrote here these definitions. But basically, bisymmetry is the only one which is not usual. So he said that we take a two-variable function from I squared to I, which is continuous, reflexive, partially strictly monotone, symmetric, and bisymmetric. It has these properties if and only if there is a continuous strictly increasing function from 0, 1 to I, so that fxy is the conjugate of the arithmetic mean.
But isn't it the same what you said before for more general?
No, first of all, it was a sequence. Second, the condition here was somehow the interplay of the variables. So this is just for two variables, and later on, it's also a historical note which I skipped, that later on it was generalized for n variable case, which is interesting, but today I will focus on the binary one. And that's what we first studied. So I don't know, maybe 5 years ago, I met with Paul Gray in a conference, and we started to talk about this. He gave a talk on this type of expressions where it is not continuity assumed, but and partial strict monotonicity, but some bijection was assumed, and what kind of properties it has. And later on, we talked about this theorem and asked which property can we avoid. And for sure, bisymmetry is very, very important, so we cannot. But any other gives a different statement, except continuity, which we stuck for a while, how we can, whether we can eliminate or not. And the result will be, okay, I show the result first, and then I come back to this. So that's what we investigated. What can we say about condition of regularity? But I know that strict monotonicity is a very important property, a very basic property, which somehow on an interval inherits some analytic property. So it's not very surprising that we have this result, but all in all, it is somewhat surprising. So and now I focus on closed intervals, but because I would like to say something from 0, 1 to I, but generally it's true for any interval. So it's not needed closeness here, but I assume that because it's easier to have the. Okay, so you take a closed proper interval. We take a function from I squared to I, which is reflexive, partially strictly monotone, symmetric, and bisymmetric. So we don't have continuity. Then there exists a continuous strictly increasing function from 0, 1 to I, so that this formula is true. So it is a quasi-arithmetic mean. And as a conclusion, we get that every function on any proper interval, which is reflexive, partially strictly monotone, symmetric, and bisymmetric, is continuous. Moreover, it is a quasi-arithmetic mean. Okay, I go back to the previous one because it might be interesting later on. So we can also take some two constants here. It's really easy. Observation is that if we take any constants, any real constants, then it's called weighted, or maybe I just call it weighted quasi-sum. But so this weighted quasi-sum is bisymmetric from all alpha and beta. It is just a short algebraic verification. Strictly increasing if alpha and beta are positive. If both are negative, then it's strictly decreasing, and so on. So it's easy. Reflexive if the sum of the two parameters are 1, and symmetric if alpha and beta are equal. So it's very, very, very simple. Just good to know. Okay. So that was the theorem, and as I mentioned, in two variable we can change monotonicity to increasingness. So it's the same. Acel originally said monotonicity, but automatically he think on increasingness in this case. But maybe many things. So his proof is not very well written, let's say, but all idea or essential idea was there. Most probably everything was as was in his mind. Okay, I talk about his proof because in this talk I will talk about 3 proofs. Well, this is the first one, this result, how continuity to come, because I think all are nice elementary analysis what is used, and the second one is connected to fractal geometry or fractals. So somehow. So let's see. So how Acel did. Because we tried to find a local behavior, but we were not able to. And finally, we recognized that the right way is following Acel as far as we can. And then we cannot, then we should do something else. And so Acel also turned to the closed interval case, and he defined the function from 0, 1 to AB, recursively defined only on the dyadic numbers first. So and he introduced this notation just to make it much simpler, writing all f and f and f. So f0 in his definition, f0 is A, f1 is B, the two endpoints of the intervals, and f1 half is the composition. F1 force is when I compose A, I always take the half of the previous one, and when I take B, then the other. I always split the split the interval into 4, and when I use A, then I take the first force and the third force when I take B as a composition, and so forth. So the first challenge might be to prove that this is a good definition. So it's well defined. That's what Acél did. Basically, this is, so if someone goes deeper in the proof, then he can realize, or she can realize that basically bisymmetry is the reason of the well-definedness of this. And also reflexive symmetry is used, but the heart of the proof of well-definedness is bisymmetry. So bisymmetry somehow inherits this property that this is a well-defined definition. It's not trivial, so on their own. And he also proved that it is strictly increasing. It's not very hard. If we have f, which is strictly increasing, doesn't use any continuity. So the second point is that ft is dense in AB, then f is continuous. Well, it is really a standard trick. So and we use it many times. So I just write down the proof shortly. So let x be a point in which is not a dyadic number. Then we have two dyadic sequence, one from above, one from below, which tends to the n, and we take the limit of the images L and R, left and right. So by strictly increasing next, we know that L is smaller than R. What we would like to show is that L is equal to R. If AFD is dense, then there cannot have this case, because then this is an empty set. So it's okay. I think it's very, very simple, right? Anyway, so this is the idea what Acél original argument used. So if f is continuous, then capital F is continuous, so FD is dense. And he used it in the following way. If L is smaller than R, then he take the composition of with L. So it's L composition L is L by reflexivity. This is by strictly increasingness in between this one and R, which is R composition R. Okay, so he takes the sequences F, D, and K, and capital D and K, so he selects some subsequence so that this sum, this arithmetic mean, is bigger than X. It's infinitely many times bigger than X, or infinitely many times larger than X. So one of them is good. So let's take it's bigger than X. Then the composition, which is equal to this one by definition, is bigger than R. But in this sense, L composition R is bigger than R, which is a contradiction by this. So this was the original argument. That's what we can apply, because we don't have a limit object in this sense. So we cannot, we have some limits, but we don't have continuity. So instead of that, we assume that FD is not dense in AB. That's what we would like to get as a contradiction, because then we are done. So if we take FD, the closure of FD, which is uncountable, it has uncountably many two-sided accumulation points. That's what is simple. So first what is two-sided accumulation point? So any set you take, and we say that we can distinguish the elements into three classes. One of them, that alpha of H is a set. Alpha of H is isolated if you can find an interval where there is no other point of H. One-sided accumulation points if you have only at least a half interval, including at the endpoint alpha. which is empty, and two-sided accumulation point if you don't have this type of property, so you can. And in fact, both this one, the one-sided accumulation point, and these isolated points are countable sets. So if you have an uncountable set, then and you eliminate these two objects, then you have uncountably with many two-sided accumulation points. So this is just a tiny observation, but it was, yeah, I just said that you have an empty closure. You have at least you have uncountably many two-sided accumulation points at least. Okay. Anyway, so yes, so we repeat the idea of Acel at this point. So empty is not dense in AB. Then we have a Z in 0, 1, so that you can find a dyadic sequence from below and from above, so that the limit of the images are not the same. Okay, let's call it X and Y, not L and R as now. X and Y are independent from the choice of the dyadic sequence. If you take it from below, then you always get X, and if you take it from above, then you always get Y. And now this is the main observation. If you take any two two-sided accumulation points, two different, then if you take this interval X composition alpha, Y composition alpha, and the other interval X composition beta and Y composition beta, they are empty. And this is the heart of the proof. And how we can prove it? We change to X and Y to dyadics, and very similar idea, but not similar, but somewhat similar idea what was Acel argument. We can prove that not only these, but immediately for large enough N and M, these two intervals are disjoint. Okay, so what does it mean? It means that it contains uncountably many accumulation points, and by this reasoning, it has uncountably many disjoint proper intervals, which is impossible. So at the necessary sense, so at small f should be continuous, and capital F has continuous. So we are done with that. Okay, so what was Acel's next step? Acel's next step was that, assuming the continuity, he assumed partial strictly monotonicity and bisymmetry and continuity. And he said that if F is reflexive, this was the first step, then somehow he can manage to build up another function where also symmetry is, can be assumed. So from F, not an inverse, but somewhat as an inverse, he can define. Maybe I can tell about this idea. So the original idea of Acel was that he defined a function. So I have originally F, and he defined a G so that F Gxy is equal to Z if F satisfies that and he take any A, but it's fixed. Ax F of Y A is equals to F of A Z F of ZA. So he take an X and Y and he solves that in Z. And if he cannot find the Z, then he say that okay, then Gxy is equal to Z. It's not really an inverse, but something like this is in heart. But if he define an inverse, then it ruins everything. So it's not, inverse is not the right option. And why he has this? Because he has continuity. So this is a strictly increasing function. Somewhere it hits this value. So that's basically the reason why you always can have a solution. We always have only one solution by strictly increasingness, but because we don't have continuity, we cannot solve this, and it ruins the whole structure. So I cannot go in this direction further. It would be nice, but all in all, what he proved with this G, he can have the arithmetic quasi-arithmetic mean expression, and turning it back, it turns out that there exists an F, which is one variable function strictly monotone or strictly increasing, continuous, and there exists an R which is not 0 or 1, so that this weighted quasi-arithmetic mean expression is true. So it's okay. The other one, there exists some constants. So he went further. Then he eliminates also symmetry and also reflexivity. Again, he can push it back to this. The previous one, so step by step, he proved that. So he found that there exist three constants, so that the A times B is not equal to 0. So none of them is 0, and the strictly increasing, strictly monotone function f, so that fxy can be expressed in this way. Okay. So it is a good question. Which one inherits further? So, So it really eliminates what I wrote.
Yes.
Very nice. And if I go back, it's there. Oh,
Yes.
very clever. So yeah. So these results motivates the question. Please check the numbers 7 and 8. So this is for the weighted quasi-arithmetic mean, and this one I call weighted quasi-sum. So okay. So if you have a question, is it true that every reflexive partially monotone and bisymmetric function f is automatically continuous and satisfy the weighted quasi-arithmetic mean expression? And the other one is it true that every partially strictly monotone function, which bisymmetric function, is automatically continuous? So this is much stronger than this one is in English. And the short answer to the second question is no. So it may be not so much surprising, but for a while I believe that everything can. So bisymmetry can be so strong that maybe it would be much more surprising if I say yes, but it's not the truth. Okay, and the construction behind. So now I turn to the answer no, how we get it, and basically this is what I will discuss a bit more details. But maybe for some of you this is well-known results, but I hope it is new for some of you. So I take a countable subfield of which contains Q, and the subfield of R, because now we are in the reals. And take a non-degenerate closed interval. Closeness is again not very important, but I assumed at the beginning, so I go with it. And I would like to construct a set K, which is perfect. Every finite subset of K is linearly independent over F. This is the most important property in our proof. But also the others are important. So it has Lebesgue measure 0, and so it's nowhere dense. It's equivalent to that. And additionally, I take these conditions because I originally think that this is the most important part of the proof, but it turned out that this is not needed in the final version of the proof. But I think it's very, very interesting properties. So the Hausdorff dimension and the upper box dimension of K is 0, and consequently this is also true. So I can iterate this process to add to take alpha of this set plus beta of this set, and it's still 0 dimensional, and so on and so on and so on. So it is important we are able to repeat. So I will talk about a bit of this construction. This construction is a Cantor type chain. Who don't know this? Who knows this statement? Maybe all of you knows, no? So this was the first proof was by von Neumann of this statement. Okay, that time these were not studied so far, but a perfect set which is nowhere dense. Maybe Lebesgue measurability was also studied, but this property was first studied by von Neumann, and then Michalski make it much more general. So I'm not sure I understand all details of his proof. So instead of that, I found out another proof which contains by Michalski. So it's not a new thing for sure. And this type of idea was used by Kekis. So I asked Ricci Balka and Máté Pálfi about this, where I can find a good reference, and both told me, see Kekis. So it is well known there, but But what Michalski did, he take instead of linear independence. Later on, it's easier to explain what he did. Okay, so the construction is a counter type chain with two ingredients. At end step, I will exclude one prescribed non-trivial affiner relation, and the scale decreases so fast that the final step, the upper box dimension is 0.
What is that affiner?
Affiner, okay. Affiner means that you have a kind of expression of this one where the coefficients are from the field F. Okay. So I have it also works with my finger.
Oh.
It's very interesting, but you okay, much I just recognized.
Whatever.
Yes. So F is countable. So we can enumerate, that's the reason why we take countable field. So we enumerate all non-trivial field, finite affiner relations, which is in this type of relations. And we repeat it, so we list it in a way that this list contains all of this expression infinitely many times. So we go back to this later on. That's an important point. So, and we choose a rapidly decreasing scale, let's say 2 to the n squared, 2 to the minus n squared. And now we construct a family inductively. So the first one is the interval itself. And then in each step, we will split every interval of in into 2 parts. And we will shrink it so that this condition is true for each of the intervals. And also we should take care of this linear expression that it doesn't vanish on that. So any point, if you take n points from n different intervals, it cannot satisfy that if I put it here in the variables, it cannot satisfy that. So I choose in this way. Okay, so now we take it in a step. So in it contains these intervals, and I have the next relation. So if this kn, how many variables I have, is bigger than the number of intervals, I go further, because after certain points I have enough interval to check this, and this relation will come back, right? So if 2 to the n is bigger than kn, then I do the following. I take smaller intervals than the original division, so that this product and the intersection of ln equal to 0, this is a hyperplane. This is a hyperplane. It doesn't touch the product of these intervals. So basically, at the end, I will put x1, xn from this, so that this cannot be 0. That's the aim, and that's why I need this condition that if I intersect with a hyperplane, it doesn't touch this product. And also I take care of the length of the intervals. So I shrink it if it's needed, and at the end I will split into 2 disjoint intervals, because I would like to keep that condition that in each step I have 2 to the n intervals, n plus 1. So okay, so let's check the properties. So every interval has 2 descendants, and the diameter tends to 0. So I take the limit object. So it is a non-empty compact set, and it has no isolated points because of this diameter condition. So K is perfect, and this may be the most important property, which is not. Well, I think it's not clear. So if I have, so I suppose that we have 2 different elements, and we have a non-trivial relation. I have to show that it cannot satisfy this, that it is equal to 0. L appears infinitely many times, so there, for large enough n, there are intervals where these elements are in distinct intervals. And then this cannot be satisfied. So I think it's clear. So the elements of K are linearly independent over F. Are there any questions? Okay. Yeah, by construction, also, again, it's clear that the Lebesgue measure of the set is 0. And as it is closed, it cannot contain an interval, so it is nowhere dense. Okay, so what about the dimensionality? As I said, it's not very, very important. I just write down shortly that why the Hausdorff measure of this set is 0 and why the upper box dimension is 0. For us, maybe the second one is more important. So if I take any R, it is between two scales, ln and lm plus 1. So we can, in this way, we can estimate what is this ratio, and it turns out that it should be smaller than n plus 1 over s squared, so it tends to 0. Why I put the second part? So originally I started with this one and I stuck, because the reason is that this doesn't imply immediately that this one is also 0. Why it is so? So I think it's a very interesting phenomenon that how we how we estimate the Hausdorff dimension of this sum. We take the image as under this Lipschitz map of K times K, and if we have this one, then we know that this has also 0 dimension. But in fact, this is false in general. If you just only know that the dimension of K is 0, and now I try to explain, I don't go into this example, but in Falconer's book, you can find an example of two sets, E and F, so that both has 0 dimension, but the product of them has bigger than 1 dimension. Moreover, E plus F in this construction is large itself. So it's not only that after this maybe we can get 0, but also the sum. And one can easily get an example if you take the union of them. You can check that this A has 0 dimension, but the sum of that is big. So instead of that, we need the product formula. So I borrowed from the book of Falconer. So if you have the box dimension, which is 0, then the product can be estimated by this formula, which is 0 if both are 0. Okay, I skip the condition that both are 0 because I will apply it for this one. So, and in this case, both products has 0 dimension and inherits this property. So this way we are done. So let's go back to is it clear what was explained? Yes, I think this is a very interesting. And for me, it was really surprising that you can have a 0. I really expect that if you have a zero dimensional set, you can make any product or any sum of them, which is not. But many of you might know it very well. But anyway, so I start the construction. So I take a K from the theorem. So
what are you constructing now?
I'm constructing now first a counterexample I will construct, which is not continuous, but it has bisymmetry and strictly increasingness. And the basic idea will be that I use these quasi-sums, but avoiding continuity property. And for this, I need a very nice set, or nice set in some sense, nice set, which is not an interval, but it has some similar properties than an interval, but it's small and linearly independent. The elements are linearly independent. It's possible. But it's not all elements are linearly independent, but the first step, the K, has this. So K has all of the properties. We don't need the 0 dimensionality, but we have that nowhere dense and perfect and linearly independent. The elements are linearly independent. Okay, so H0 I denote, which is now K is taken from between 1 and 2. And I fixed out first for the first side an alpha and beta which is bigger than 1. Why I do that? Because it's easier to see that if you have an H0 and you add that, you take alpha times H0 plus beta times H0, then it is in another interval, so basically disjoints, but it's as we assume linear independence, it will come without this extra assumption of bigger than 1.
So how do you choose K or
K was the what we get from the theorem.
from the student? Okay, fine.
So
Yeah,
this one.
okay.
Oh, sorry.
No, I don't see them.
I was too fast in both directions. So this one.
Yeah.
So perfect. And this tool is not needed. It is just very interesting for me. So maybe that's why in the proof it's not needed, but alternatively you can use also these facts to find the.
And you can assume that is a subset of the 0, 1, and 2.
1 and 2, yes.
Okay.
That's important that I assume. Yeah. Just a moment. I arrive back. Yes. So I take H0 like this, and then recursively I define HI. So I take the previous one plus this sum. And then finally I take the union of all of them. Okay, so it has some very interesting properties, very nice properties. Okay, this is an inclusion, and H and as a HI as well are perfect sets and of dimension 0. Why it is perfect? Because after a while, because of this condition, you go out from every interval. Leave left every interval with that part. Okay. So after a while, it is fixed what you can see in the picture, on a bounded interval. So that's why it is perfect. Every element of H can be uniquely written as a linear combination of elements of H0 with non-negative coefficients. So this non-negativity is basically the heart of this one, because, and here I can use that this is bigger than 0. These are bigger than 0. And finally, I take H prime because a closed set cannot. So now my aim is to find the bijection from 0 infinity to a set of this type, but this is a closed set. So at the end of endpoints, I might have some trouble. So I eliminate the right endpoints. So is it clear what right endpoints I mean?
It's the left endpoints of a complementary interval.
Yeah, exactly. Or maybe I can say with the previous notation that the one-sided accumulation one-sided accumulation points I eliminate from this set. But you're right, the complement is are some intervals, so and the left endpoints of these intervals are eliminated. Exactly. So this set has again a countable cardinality, cardinality. It contains no interval, and by this trick, it is basically the counter Debye-Stair, the inverse of the counter Debye-Stair function, what we take here. So we take a 0 infinity to H prime, and it is a strictly increasing bijection, and this is the heart of the construction. So we take now fxy is defined with f inverse alpha x plus beta y. It is a function from 0 infinity squared to 0 infinity, defined in this way. And it has the following properties. Partially strictly increasing. It is clear because, as we discussed, if alpha and beta are bigger than 0, then it's partially strictly increasing. So that's why I talked about that easy properties at the beginning. F is bisymmetric. And this is the harder part. So for every x, let's say in this way first, every x in 0 infinity, the operation fx dot is not continuous. So the first three, there were one more, not reflexivity. Yeah, symmetry. If you have alpha and beta are equal to 0, then it's symmetric for sure. Again. But this one is not clear. So the last one is also true. And if f is continuous, then there exists a capital L, such that for every z in L infinity, there exists a y in 0 infinity, such that this is true. This means continuity. So this means this property, and this we should discuss a bit. So let U0 in H0, U in H0, so the original set where all elements are linearly independent, such that the coefficient of fx is positive, non-zero, while the coefficient of fz is 0. If we can find such an element, which is possible because we have many z's, then we are in a contradiction because we have non-negative coefficients on this. So this, since the coefficients of u in fy cannot be can only be non-negative, this gives a contradiction. This also means that we can state in much stronger way because you can find such a z, countably many such z, which has this property. Okay, so the theorem, what we get is the following. For every alpha beta which is rational, there exists a bisymmetric strictly increasing function that is not continuous. More precisely, for every x0 and y0, this is not continuous. Yeah, again, I put this notation remark here. If alpha and beta symmetry is not an important property in this construction, we can a bit make it stronger. So it is not needed that they are bigger than 1, but the sum should be bigger than 1. Not too much, but you can also make it stronger so that the sum is not 1. So not the reflexive case. If the sum is smaller than 1, but they are positive, but not 1, this means that you can make the same construction, but not for 1, 2, but for 1, 1/2, and you go closer and closer to 0. So the same construction, but instead of going to the infinity. And also, as I mentioned, contain countably many points of discontinuity, each section. I should stop more or less. Right?
Two more
minutes. Then I will not go to the what is here. Yeah. So the reflexive case is what is exactly the other open question. The other open question is that is it true that every reflexive partially strictly monotonic and bisymmetric function is automatically continuous? So we have this form. And the answer, I don't know. What I know is that even this one I cannot prove. So if we have this type of thing, I really expect that if you have two elements except y, which are not x is smaller than y, and for instance, this one is true, so no symmetry, then you have for all u smaller than v, this property inherits, because this has this property. But I was not able to prove it. But this leads to a question. What if we have at least one point, one pair of points where we have symmetry? What does this imply? And I just tell finally this will be the end. The proof I will skip them. So if I take a proper interval, reflexive partially strictly increasingness and bisymmetry, so symmetry is not there. If you also eliminate reflexivity, we saw that its continuity is not necessarily assumed or inherited. And we assume that at one point, one pair of points, we have symmetry, then symmetry and continuity comes. So we get back to the quasi-arithmetic mean structure. And we get this dichotomy basically. So every bisymmetry strictly increasing reflexive binary function is either symmetric or nowhere symmetric. This is the end of this story. Well, very shortly, the proof is based on these three properties. So one of them, if you have u and v, then in between you have very symmetry. So if you take u and v symmetric, then everywhere is in between it's also symmetry. So you have an interval where it is symmetric. If these two intervals intersect, then it's whole. It's not a trivial statement. So if for two intervals, each elements are interchangeable, and they intersect then for all elements. And finally, if you have symmetry on I1 and I2, not necessarily maybe disjoint, then in between you can find an interval where where you take this composition, where it is also symmetry. The elements on that small interval. And using this, you can you can introduce a equivalency relation so that FAB equal to FBA for some elements, and this equivalency relation splits the interval into equivalency classes. Equivalency classes are intervals, moreover closed intervals. That's a very important observation. And finally, you can split this into two cases. One of them you have many intervals, more than omega. Then you are in the situation that you have too many intervals again, or you have at most omega is the number of this type of intervals, and then you somehow cover the 0, 1 or any interval by closed intervals. Disjoint closed intervals, countably many, and this idea is basically why it is not possible is a counter diagonal method. But Sierpinski told a very nice theorem. Do I have time to say it, or let's keep it?
Well, yeah.
This is the last point. So this theorem says the following: if you have a compact connected Hausdorff space continuum, and if X has a countable cover by pairwise disjoint closed subsets, then at most one of the sets Xi is non-empty, which means that it is the whole. So it's very strangely written in this way, but Sierpinski told in this way. So if you have this property that you cover a continuum by disjoint closed subsets, then one of them is basically, only one remains basically. And then this is basically what we need, because this means that on the whole interval it is symmetry. You have. Thank you for the kind attention.
Thank you very much. Questions?
Yes, please.
Do you have similar results for the multivariable case?
Yes, some.
So
So we have basically so the positive result was that if you have symmetry, all of these properties can be introduced by symmetry as well. Instead of 2, you take n and times these terms. Then you can take the first ones in the first. Yeah, exactly, the matrix form. And then you have we can prove that it is a very new. So it's for a while I was not sure on this, but it turned out that this is true. Also continuity in the symmetric case, and on the non-symmetric case I also don't know. In reflexive non-symmetric case I don't know anything, and also the counter example can be applied. Instead of alpha and beta, you take alpha 1, alpha n. Some are not to 1. All are positive. Then you can construct such a function which is not continuous, bisymmetric, and strictly increasing. So this is basically the same construction. So yes, what we have can be applied in the multivariate case. But which I don't know is the original characterization. Can we avoid continuity? The Kolmogorov-Naumov definite characterization.
More questions? I have a semi-related question regarding to this set K, which every element is linearly independent. So so in the construction it has 0 dimension, so it's very, very tiny. But my question is, do you know that how large this set can be?
Yeah, that's a very. I don't know, but I don't know. That's a very good question. So because as an extra condition, I have to assume that these intervals are very, very small, so that I get. But if I avoid that, I don't know how large can it be. It's a very good question.
I would get that this must be very small set. So
maybe it's not
needed
any condition on the length of the interval itself, right? Yeah, maybe you're right. Right.
Okay.
I have one more comment, because I mentioned that I will tell what Bisymmetry's original statement was, or one of his statements was. He assumed, instead of, you may remember, ln equal to 0 was a hyperplane. And instead of that, he take an algebraic curve. And for any algebraic curve, a system of curves he take, he still has these results. It's much more general than only hyperplanes or linear functions. That was my comment. So it's much more complicated, and still I'm struggling to say that I completely understand. That's why I may build up another group, which might be also a standard thing, but I didn't find that.